It is day 5 of November, and for some reason I woke up today and decided, yes, we're gonna do the hardest one yet. Anyways, the prompt for today is lovely, and I thought, what is more lovely than having a porcelain coffee cup with coffee being stirred? It's too hard. Anyways, in Blender, I'm going to delete everything GeoNodes, make it a GeoNodes object, and delete. I'm gonna use a cylinder, because cylinders are pretty close to cups, and I don't want the top of this exposed, because you gotta be able to drink out of this. So I'm gonna delete and get rid of the top. Increase the vertices, increase the side segments, and the reason I want these like side segments is I'm going to reshape the cup, which needs geometry. And I want to alter the position with a custom function. Isn't that always the way? So I'm going to multiply by a combined vector. And the important thing is we're going to keep z equal to 1, which keeps its kind of like verticality, but we're going to be messing with x and y. I'm going to make my cup like 1 meter tall, and we can use this information to actually reshape it. So we know that z goes from negative 0.5 to 0.5. As you can see here, it's 1 unit tall. So I'm going to map range this from negative 0.5 to 0.5, connect that to the x, connect it to the y, kind of like a goblet or something like that. Either way, we can reshape this now with RGB curves, which is kind of like the most intuitive way to reshape. Bring up the minimum to kind of make a flat bottom if you want that, and just play around with this until you like the way that it looks. This is a pretty wide cup, but I think I've seen cappuccinos look like that. I'm just going to make it a bit thinner with a multiplication. One more thing is it should have some thickness and a rim. And while I would like to do this completely in geometry nodes, that isn't really practical while we don't have a bevel node, so I'm also going to use another modifier. So I'm going to extrude this mesh, not by individual, but one thing you're going to notice is that there's no like interior, like we've just made a lip, and the way we fix that is we flip the faces here, we join it. So now we have the original plus the extruded mesh, and to not have overlapping vertices, you merge by distance. And now we're going to bring in our sad bevel modifier, which you can see kind of gives us a nice slip. But again, I would have really liked to do this in geometry nodes. I'm going to set shade smooth, and there you go. Take all of this, Control G to make it a node group. And to me, a cup has kind of like a reddish, pinkish, bright vibe. Next thing is I want the plate that this is sitting on. Instead of a cylinder, a plate kind of looks like a circle, and add some vertices. And really what I want to do is I want to go like this and like that. So I'm going to extrude upwards by the edges so that we don't get that top face. We can make this thing a bit wider by scaling the elements of the edges. Extrude one more time. Again, we're extruding the very top of this, kind of like eating inwards. So I'm just going to define this vector to go upwards. And once again, scale the elements of the top. So we got ourselves a plate. I'm going to do the same thing as before, where we are going to extrude our mesh just to make it a bit thicker. Flip faces, join this, and then merge by distance. Now, obviously, you know this is procedural, but just to emphasize it, you know, we can make a square plate, we can make a pentagon plate, Control G, which to me kind of feels yellow. I don't really know why. So we got our cup, we got our plate. I'm going to join them together and then basically scale up the plate. So there's pretty much all of our geometry, but I want to make one more thing, which is going to be a straw. Straw is basically a cylinder. Make this thing way thinner, and we are going to delete. Well, I guess we just don't need the fill type, which will get rid of the top and the bottom. This is kind of like small enough that you could get away without a solidify like we've been doing, but I'm just going to do it anyways and merge by distance. Make that shade smooth. Control G, and this straw is definitely red. So now I want to take my straw and kind of like rotate it in a circle, and we're going to say that this is what is driving the fluid motion. I'm going to rotate it a bit, I guess, on the x-axis, so it's coming in at an angle. And what's going to make this a lot easier is if this origin is centered on the middle of the straw, because we're going to need this location anyways. Z is equal to 0. And now let's do our rotation, and then we can bring it back up. So we're going to combine x, y, z, and we know whenever we're talking about circles, we're basically talking about sine and cosine. Connect. We're going to have this animate over time, which is going to go way too fast. Take this and divide by, let's say, 15. So now it is stirring nice and slowly. Now this person must be stupid because the straw is basically like rimming it, which tells me that it needs to be a bit smaller. We are going to scale it by a tinier amount so that this is inside our cup. And then finally, we can take this and then transform it upwards. The rotation here is kind of like on a constant axis, like it's the Earth rotating around the sun. It's not a flat Earth, allegedly. What I want to do is I want to add like some randomness to the rotation. Noise texture as our source of randomness, one dimensional. Take the W slider, and we are going to take the time by, let's say, 20. So it goes a bit slower. Take this color, plug it into the rotation, which you can see randomizes it a little. So I'm going to first of all center it by subtracting 0.5, which makes it less intense. And more so, I'm going to make sure that it's going slower. We could also try like maybe offsetting the position a little. Let's try that. So I'm going to add this component as well, scale this, and maybe contribute 20%. So that is looking pretty natural. And one more super important thing, make sure to do this, is we are going to multiply this by 1, 1, and then 0. So it doesn't go up and down on the z-axis. And you're wondering, why is that important? Because it's going to make our fluid calculation infinitely easier. Node groups out of the wazoo, and we can call this movement. Anyway, now is the very hard part of the tutorial where we are going to do a fluid simulation. I actually made a dedicated like 1-hour video to fluid simulation. That is a must watch. I'll say it's a must watch. We're going to add vertices. And the reason I'm adding a circle is I want you to think of this as where we are spawning our fluid particles. And because the straw is super relevant to this, I'm going to make sure to join this and view it so that we can see our straw basically going through the fluid. I'm just going to put this off to the side and frame it. Distribute points on faces. These are going to be our fluid particles. Bring this up a lot, and you're going to see that a lot of these fluid particles are like overlapping or intersecting. The main thing you have to know about fluid, or this approach to it, is that each particle wants to move away from each other. Point is, we are going to change this to Poisson disk, which makes sure none of these are intersecting, and our non-intersection value, I'm going to make a parameter. So I'm going to up the density to, let's say, 1,000. As I increase this, it's going to get rid of those intersections. We're going to want to set point radius to this amount. So you can see that as I shrink it, the points also shrink, but they're staying apart from each other. There's also like a lot of gaps, like here, here. I mean, really a fluid kind of takes the shape of its container. That's kind of the point. So what I want you to do is think of this as our initial condition, and now the rest of it is solving or simulating the fluid. Theory of collision, super quickly. If two particles are kind of like this, they're overlapping, that means they're colliding. Mathematically, how do we know this? Well, there's two particles here and here. We're going to say that they have the same radius for simplicity, and we say that these are colliding if 2 times the radius is greater than the distance in between them, right? Because if we had two particles separate, twice the radius is nowhere near the distance. In other words, I'm going to use index of nearest because it's going to look at the nearest point, which is the one we want to evaluate, its position. And like we said, what we care about is the distance between these. So position versus position of the nearest. Take that distance, and we want to see how it compares to 2 times the radius. If 2 times the radius is greater than the distance, under that condition, what I want to do is I want to actually move these points to get rid of the collision. So this point should kind of go this way. This point should go this way. I'm going to set position by these points that are overlapping. And then the question is, what is this vector that we want to like move towards? We want the direction going away from it. Long story short, we subtract the original position from the nearest neighbor position. I'm going to normalize it so we only care about the direction and not the magnitude. And then the magnitude should be 2 times the radius minus the distance, which again is going to be a positive quantity. So I'm going to now scale this vector that has a scale of 1 by this. So I'm going to plug this into the offset because we're moving the particles, and immediately you can see it's doing something. It's not clear if it's working. To actually evaluate this, we can take all of this and also make it its own node group. I'm going to make this orange. What we need to do is do a lot of collisions, because kind of just doing this one time doesn't really guarantee anything, right? The particles could be moving and colliding again. And the theory is the more collision checks we do, the better this is going to be. So with a repeat zone, I'm going to put our collision inside of here so we can do our collision none at all, or 1 time, 2 times, 3 times, etc. And you can see that as I up the iterations, you can see they're actually trying to get away from each other. And actually a minor correction, I don't think we need this normalized because we need to know the just direction / magnitude distance between them. And you're seeing, okay, this is doing a pretty good job, but again, it doesn't look perfect. And that's because we're doing our collision checks basically 16 times, but then we're not like doing any kind of update where we're saying use your new positions to do another collision check, etc. So what we're going to need is a simulation zone. So make sure the simulation zone feeds into the repeat zone. So the simulation zone is going frame by frame by frame, and then per frame we're doing these repeat zones. So you can see when I play this, they're actually moving away from each other really well. Next is we have our boundary conditions. So these are inside a petri dish, but as they expand, you can see that they kind of go outside of this original petri dish, and this should not be allowed. In other words, if a point is outside our petri dish, we just need to move it back. It's a bit more specific than that. So if this is the boundary, the last place it can be is kind of kissing this boundary. This is the last time where it's inside. If we move it even a little, it's no longer inside. The way we describe this mathematically is if this overall boundary has a radius of 1, we actually have a little less room to go because we can only go about this far along this circle because anything further doesn't work. And that is going to be 1 minus whatever our radius is. I want to look at the position and I care about its length. And I want to check if this is greater than, less than something, 1 minus the radius. So again, we're going to check if the length is greater than this quantity. We again want to move our points. So this is all like a bunch of set positions with conditionals. So under this condition, unlike before where we had to calculate a bunch of vectors or something like this is actually easier because if we have a point here, we actually know which direction it's facing in, and all we need to do is decrease its magnitude a little. We take the position, we care about its direction, so in other words, we're normalizing it, and we want to scale it by 1 minus this radius. So this is going to be the position, not the offset. And you can see the moment we do this, it's going to constrain these back in. Okay, so now we have basically our initial state, right? We have our points, and then they kind of settle to fill in the fluid. So take this, take the rest of it, Control G. For me, boundaries are very like, I don't know, they're kind of like this purple where we're saying, don't leave the boundary. Okay, so they're colliding. They're not caring about the boundary, or they are caring about the boundary. And the last thing we need to do is now these need to interact with the straw. So I'm going to join our straw back in at the end. And now we need to do some kind of condition where these are moving away from the straw. And if you've ever seen like somebody stir something, there's going to be this behavior where the fluid almost like wraps around it, and then there's this kind of like drag. Now, the way we calculate this is actually pretty similar to the way we calculated the boundary, because this straw is basically making a circular cross section, which is why I centered it, so that remains consistent. In other words, for our straw, the only thing we care about is basically its location, which is given by this. Because again, if we get rid of the translation, it is centered, and that's a consistent boundary, but we have a moving boundary. We are going to set position because we're moving points. The question is, which points are like close to this reversed boundary? We look at a particle and we calculate the distance between this and our boundary. So this is almost like a particle of its own. It's very similar. And we want to see if this distance is within some threshold. So I'm going to compare the position to our translation from before, and we care about its distance. And what we are checking is if this distance, I guess, is less than, this distance, again, is smaller than not 2 times the radius, which is what we're used to, but it's actually the radius of the straw plus the radius of the particle, which aren't necessarily the same. We want the radius, and then we want to add basically a constant value, which is going to depend on the thickness of the straw. In fact, if we go into our straw, we know what this radius is exactly, because that's our like cylinder parameter. So I'm just going to plug this in right here so we can control it. So 0.013, connect this here, and connect that to our addition. I plugged in the wrong thing. Get rid of that and plug this into the correct addition. And I might have been saying it backwards before, since what we did before is we checked if 2 times the radius, or this modified term, is greater than the distance. We are going to set position, and the new position it should have, again, is we're just kind of nudging it this way. We are going to take the difference vector that tells us what direction to go, and then scale it by like the distance minus something. So I believe we take this like radius addition term, and we are going to subtract the distance, which again is a positive quantity. We need to know kind of the direction we're going in, which is going to be the position of the particle minus this translation, which again is the position of the straw. And I'm going to take this, and we are going to scale it by this amount. And for the people that have been yelling at me for the last like 10 minutes that I calculated the collisions wrong, I just realized, by the way, the collisions work, but we could have them be a bit more stable. In the collision, you can take our scaling, and you can take this and divide it by 2. Because again, I said if there's a collision, each one should move in the opposite direction by half. Technically, this isn't like necessary to guarantee like a no collisions in the end, but I do believe it adds some stability and makes it like converge faster. Take this, connect it to the offset, and if we play this, you can see, woohoo, it doesn't work. Why does it not work? Good question. I think basically what's happening is the straw's not big enough, or maybe it's moving too fast to do any kinds of collisions. We can check by increasing the straw radius, and in fact, the particles are now avoiding it, and you can see it's kind of like leaving this trail behind that we talked about. One thing I want to do is I want to take everything we did here, Control G, and objects are definitely red. I am sure about that. And now that we have our 3 operations that are basically dictating how things should like resolve, we want to think about the order of this. Is this the correct order? And the answer is actually no. Ideally, what we want is we want these particles to collide with each other. We then want to collide with the object, so none of them are occupying that space. And all of this might push particles outside the boundary. So at the very end, we do the boundary. In other words, I'm just going to put the boundary at the end of this. And for now, I'm going to increase the size of our straw just so we can see what's going on. You can see that this stuff is generally working, but it's still not really behaving like a fluid. It's just kind of like moving out of the way and then colliding. And that's because this movement is basically just like collisions happening. There's like no sense of momentum, which is the main thing that like drives this world. Things that are moving tend to keep moving, not just like resolve and stop. In other words, before we do all of these like checks and everything, I want this to be able to like move based on some velocity. I'm going to set position by an offset that I'm going to call V. And then the question is, what is velocity? I haven't defined it. Velocity is going to be the new position minus the old position, which makes sense. And then this position update is basically happening based on these conditions. So let me show you what I mean. Before we do anything, or before we do any of our collision checks, I want to store what I'm going to call old, or like the old position, or the position. We then do our velocity movement, and then we do our like collision checks. After this, we calculate the new velocity. So we are going to call this V for velocity, position minus the old position. And this is going to be our updated velocity. In other words, on the first frame, we store our old or initial position. We then move by the velocity that isn't defined yet, so it's not going to move at all. We solve for collisions and boundaries, whatever, which will move the particles. And then that movement is going to be stored as a velocity, where on the next frame, it's going to move by that velocity. It's going to conserve that momentum. Should make this behave much more like a fluid. And now you can see it's dynamic and spinning and actually, I don't know, it's reactive in a sense. Inside the movement, I'm going to take our frame division. Let's actually make that a property. And I'm going to divide it by a smaller number, which means straws moving faster and fluids more chaotic, which also means that this is now becoming unstable. And that's because we don't have enough time to like really calculate for this. So if we kind of like double the time, what we should be doing is we should be taking twice as long to calculate this. So I'm going to run our simulation nodes for, let's say, 250 frames. And after we do that, we are going to play back our simulation at 2 times the speed. So again, here's our simulation. It's acting really slowly. We play this not at 24 frames per second, but at 48 frames per second. So now the straw's moving faster, but the fluid is like, it had enough time to react and stuff like that. like that. But because it's basically water, especially if you go to a shit coffee shop, what we're going to do is we are going to take this velocity, and on every frame, we are going to scale it by, let's say, 99%. In other words, it kind of loses 1% energy for every single frame, which kind of behaves like friction. Let's simulate again. And it's kind of hard to tell, but I think that this is now a bit more like viscous in a sense. We need more fluid particles. The way I'm going to do this is I'm going to half the radius, which you can see now allows for many more particles, and I should just double the density so that there's more of them. As I play this, you see it resolves, and now there's like much more action going on here. Like there's these like spurts of velocity that are happening. Okay, so what I'm seeing here is basically it kind of behaves a little differently. We're almost like losing our stirring, and I think that's because we have like too much empty room, right? Like this fluid should be absolutely packed. In other words, I'm going to like basically increase the density as much as it lets me before it doesn't add particles. I'm gonna see if I can cram even more particles in here. Okay, so now we're really kind of like leveling off. It's not really going above 21,000. So more particles are good. And something I haven't considered is if we have more particles, on average, you would expect that we need more kind of like particle collisions to make sure things resolve. Other words, particles can kind of pass through each other. So I'm gonna increase this by 2. This is going to really up the simulation time. Definitely seem to be stirring a lot more than it did before. And we're gonna turn this thing into a material somehow. Again, you can always like resimulate it. Issue with turning this into a material is there's not many like coffee particles, right? There's like gaps of air in between. So if we gave this thing a material, you'd see the underside of the cup. So we need to do something a bit fancy. The way I'm gonna do this is a bit unorthodox. It might not even be allowed in your religion, but we're going to use an 𝔹𝕝𝕝, which seems like a really weird thing to do. Well, let me show you why I'm doing it. I'm going to increase the subdivisions, which you can see gives us like a very well-distributed circle in terms of geometry. I'm going to basically cut this thing in half. And the easiest way to do that is we are going to delete everything like beneath the X and Y plane. So I'm gonna look at the position, I'm gonna separate by X, Y, Z, and we should be able to plug in Z immediately here because some of them are negative, some of them are positive, and we're gonna keep increasing these divisions. I'm then going to take this and I'm going to scale it by 0. We basically get a circle with very, very uniform geometry where all the points are basically equally spaced. That's actually what I was going for. What I'm going to do is for each of these points, doesn't matter which one, I'm going to sample the nearest fluid particle and it's going to inherit its identity in some sense, which is kind of a weird way of saying it. And before we do any of that, we basically have to resimulate it. Very sadly, we're going to need to go to our initial condition, and I'm going to store a named attribute called like start or something like that. And this is going to store the position, which again, why are we doing this? We have the old named attribute. Well, this one's getting overwritten every single frame. I want basically an attribute that tells me where everything was in the beginning, and then we can map that onto our mesh is the idea. And now that I've done that, I can actually sample our nearest point. So I'm going to plug in our simulation for a vector that we are going to call, we have our named attribute, we are going to call this start. We are going to store that as well, and I'm going to call this chords for coordinates. You're going to see why I'm doing that in a second. Final thing, I'm going to set material to the material. So again, I called it chords. Let's see what that looks like. Okay, that didn't work. Let's do take 2. You can see in our simulation zone, it definitely stored this like start attribute stuff. So clearly we're doing something wrong somewhere. And now I'm pretty sure I know what the issue is. We're evaluating at index, which thinks that it's using the 𝔹𝕝𝕝, but really I want the index of the nearest simulations thing. And there's a node for this. It's sample index, I believe. A good way to see if this works is we can use our named attribute and see if it auto-populates. It does. Okay, so we got our start attribute. So this is what we want to store. And boom, we have our coordinate system, which you can see looks stirred. That's what we want. On the first frame, it's perfectly the position coordinates. And as we play this, you can see that there's some noise, but you can see that generally it's doing what we want, except for these like flickering points. So the question is, how do we get rid of those? Now, this is going to be kind of hard to solve without making like a higher resolution simulation, which is how you get rid of this. But for now, we can add a bit of stability by calculating the nearest edge, which won't be sensitive to an individual point. So you can see that looks much more stable than a point. And then I just thought we do have a way to average these together. This is what blur attribute does. It blurs things together. So I'm going to blur a vector. Now, sadly, this is going to get rid of some of our resolution, but you can see it's looking substantially better than before. You can choose how blurred this is. Again, the more blurred, obviously, the better stability, but you're going to lose a lot of that detail. Anyways, why did we do any of this, right? Well, the reason we did it is now we have the surface of our coffee, which is a circle, so we can just put it on top, and we have a distorting coordinate system, which means I can apply a noise texture, and you can see that's being mapped. Let me make that a bit bigger. And this is actually swirling, which actually doesn't look too bad in motion. So I'm going to use a high contrast noise here. And actually another thing I just thought of, it's kind of obvious, but if we have more resolution on our 𝔹𝕝𝕝, that should be better too. Let's add a subdivision. Okay, I don't know why I didn't think of that. That's actually much better. I'm going to use a principled BSDF, connect this here. Actually, let's just view the color, and I'm going to choose 2 kind of like coffee-like colors, where maybe this has a bit less saturation. And by the way, anything we do here is going to map in the sense of our coordinate system. So I can use a normal map, I can use whatever. So for example, I can use a bump map right here, connect that to the normal, view the BSDF. You can see that our normal map is there, which is definitely like, you know, very intense. You can see it actually adds something where it almost looks like the surface makes a bit more sense. Better lighting, I'm going to use the sky texture, which seems to work best in cycles, which makes sense to me. So again, remember that we have all this geometry we kind of like left behind. I think I want to connect the straw here. Either way, I want to take all of this and basically join it with our simulation, which we can actually move. Now that it's like baked in, there's nothing stopping us. You should be able to see that our coffee is actually stirring in a semi-believable way. So I'm going to make a straw material that's going to be very basic. It's going to be the like red straw you're used to, is getting a set material that's going to be straw. So now it's red. And don't forget to also do that for the cup and for the plate, which are getting a porcelain material, so it's more reflective. Finally, let's try bringing down the scale of our straw, which again will not affect the simulation anymore. I think coffee would be perfectly reflective, maybe a little transmissive, IOR 1.33. Now I know what you're thinking. How the fuck did we go from where we were to this? Well, basically I played with the scene more. There's too much to go over. If anybody's interested, I made a background object. This is the material for it, and I added basically a background with a subdivision surface. So there goes another day of November. I think tomorrow the prompt is lake, which I'll try to come up with something more clever than a lake and trees around it. We'll see. But if you want the blend file, there's a link in the description. If you join Patreon, you get access to 30 blend files throughout this month. That is an offer. Remember, I'm uploading between CG Matter and Default Cube alternating. I'll see you guys tomorrow.